Okay, so you can see my screen now, right? So just kind of wanted to talk about something which is sort of important for you all to realize. In regression, right? So we saw clearly that there was that there's loss function which is the squared loss, and then we talked about ridge regularization which is squared L2, and then also lasso which is L1 regularization. So that part is very clear, right? That's what happens in regression. And one thing I mentioned at the end of class last time, and I was a little bit hurried, so that's why I want to kind of redo this or just mention it again, is that classification also you can actually write as we saw two examples, logistical regression and support vector machines, two of the very popular and classifiers that really work well once you have features. And they actually can also be thought of as uh, loss function and regularization. And sometimes it may not be clear, right? So especially for SVMs, right? If you go back and if I go back and look at the SVM primal here, this is the non-linearly separable one where we have the psi i's, which are the slack variables, right? So it turns out that you can actually, this is I equal to 1 to n. So this is over the training data. And each psi I, if you look at it, right, each psi I is, this is yi, which is the label. And this is kind of the prediction, right? So this is yi hat, right? So psi I has kind of this form. And if you go ahead and put y hat to be kind of w transpose xi plus w naught over here, then you can see that if you plot y hat, so y hat, suppose you have a two class problem, y is plus one, or the labels are plus ones or minus ones. Plus ones means you have the kind of correct prediction. Minus one means that you have the incorrect prediction, right? So the actual classification loss is kind of like a step function, which is like this. And it turns out, and you can convince yourself, right, that since the psi i's are greater than or equal to 0, you can write the psi i's as max of this quantity. Okay, 0 and 1 minus yi times w transpose x I plus w naught. And if you look at this, well, if I think of this as, remember my x-axis is y hat, this is 1 minus the x-axis. So it has a slope of 1. And at y hat, it is, at y hat equal to 1, it is 0. Okay. At y hat equal to 0, it is 1. Okay. And it is linear. So no loss for correct labels. Okay. But then when you are in the margin, you start having like a linear loss. So you can think of this as an approximation. And it is a convex function, although it is not differentiable at this point. So the upshot is that this formulation is very prevalent in supervised learning, both in regression and in classification. Okay, so I kind of just wanted to repeat that today. Okay. Any questions before I move on to clustering? Okay, so today we are actually starting something different. So far, we've been looking at supervised learning. I don't think I'll talk too much about unsupervised learning in the sense of clustering and principal components analysis, but I'll give, a lecture or two on this. So let's today talk about unsupervised learning. Okay. So remember that in the supervised setting, We had the training data, and we had the xi's and the yi's, right? And typically xi is some d-dimensional input space, or you can construct a feature space. In the unsupervised setting, we just have the xi's. We don't actually have any labels, and they belong to RD. So basically, there are no labels over here. In supervised learning setting, you need labels. So, you need to have some sort of supervision available, whether it's human supervision or somebody's labeled it. And one of the issues with supervised learning is that sometimes labels can actually be hard to get. Okay. They're expensive, but if you just think about a lot of the data, let's say on the internet or so on, right? Lots and lots of web pages, lots of documents. They may not actually have any supervision. They may not be labeled in any way, but there is lots and lots of data that is available, right? So supervised learning setting sometimes suffers from the fact that there may not be two data that has the supervision, but unsupervised learning has a lot of data. And this was kind of the dominant paradigm in machine learning, okay, where you would basically have supervised learning and unsupervised learning. What actually has happened in the last 5 to 10 years is super interesting, which is all of you have seen these large language models and so on. What's happened over there is that unsupervised data, right? So just documents or just sentences, books, and so on, right? There's no labels associated with it. So, in some sense, it is the data that traditionally was used in the unsupervised learning setting. But labels have been created, right? So, for example, in next word prediction, which how a lot of the decoder LLMs work, you think about predicting the next word given the context of the word,
Sorry, your voice get disconnected. We cannot hear you.
right, can actually be used. Sometimes people will still call it unsupervised data, and sometimes people will call it self-supervised learning. Okay, so we will obviously start talking about LLMs and so on later in the class. But today we'll talk about like a very common technique for unsupervised learning, right? And that is, you know, clustering or grouping the data. Okay. So, kind of, let me just ask you, right? Suppose I have these points, and suppose I'm not, notice that I'm not putting any crosses and O's. So there's no supervision. All the data does not come with any YIs. And if I ask you the question, like, how many clusters in the data do you see? Right? I think most people would say, well, there are two clusters, right? One corresponding to this set of points, and the other corresponding to this set of points. So clustering is just kind of like an organization to organize the data that you have given into clusters, where the idea is that items or points within each cluster are more similar to each other than points which are in different clusters. Okay. So there are kind of two classes of algorithms. One is these hierarchical agglomerative clustering methods, and then there are these partitional methods. So let me talk first about the hierarchical agglomerative clustering algorithms. So let me first write it down. Okay, so it's called I already misspelled it. Hierarchical agglomerative clustering. Okay. And first, let me illustrate on this data that I have, right? So the way the algorithm works is you basically say that each point is in its own cluster. And then the whole idea about, as the name suggests, hierarchical agglomerative is to merge clusters. So in the beginning, it could be that, hey, these points get merged, then these 2 points get merged, then these 2 points get merged, these 2 points get merged, these get merged. Okay. So now if you look at it, having merged this, initially I started with 1, 2, 3, 4, 5, 6, 7, 8. 8 times 2, 16 points. There were 16 clusters in the beginning. And by performing this, 8 merges, I've gotten to 8 clusters, right? And then I can still proceed further. Maybe this is one cluster. This gets merged into one cluster. These get merged into one cluster. This gets merged into one cluster. Then you have 4 clusters left. These get merged into one cluster, and these get merged into one cluster. So you basically have 2 clusters, which is kind of what we saw in the beginning, right? And what you can do is you can actually arrange, many times you can arrange these points. So if I put these points over here, I can actually build a tree out of it. 1, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? So if I follow the sequence of merges that I had done before, right, I'm merging, first I merge these two, then these two, then these two. So I'm kind of building this tree, and it's a hierarchical tree, and that's why the name hierarchical agglomerative clustering. Hierarchical because it builds a hierarchical tree, and agglomerative because it is kind of bottom up. Okay, and if typically it all goes all the way to when you have just one point, right? And you can basically cut it over here and you will get these points. So this is not the two-dimensional representation. This is just building what's called a dendrogram, okay, or a hierarchical tree. Okay, so how would we write the algorithm for this? Well, first, what we are given is endpoints, and remember, each of them is d-dimensional. Xi belongs to Rd. Okay, and what we will do is the number of clusters we'll initialize to n. Like I said, each point is its own cluster, right? And Ci is the ith cluster. So initially, each point is its own cluster, and there are n clusters. And the way it works is that suppose you want to get to k clusters, right? So the method, the way it'll work is while c is greater than equal to k, where k is something like 2 or 5 or whatever you need it to be. At each step, what it'll do is it'll find the nearest pair of clusters, distinct clusters, Ci and Cj, and then it'll merge Ci and Cj. Okay, and suppose we call the merge cluster Ci. Let me just make sure that. Okay, and we can delete Cj because all those points are now in Ci. And then we decrement C. So C goes to C minus 1, and that's the algorithm. Okay, so that's how you build an this hierarchical agglomerative clustering proceeds. It's actually quite an expensive method, right? Because if you look at the method, one of the things that needs to be done is you need to find the nearest pair of clusters. Okay, so in the beginning, how many pairs are there? Remember that the number of points is n. So there are n choose 2 pairs. So order n square pairs. So at each step, you actually, the first step, you need to do n square, and then you need to do n minus 1 square, and so on. So the complexity of this is actually cubic. So it's a bit expensive. And then, of course, the other big part is, well, how do you define nearest? Well, you could use a measure of distance like Euclidean distance, or instead of working with distances, you can work with things like cosine similarity, which are used when you work with text documents. But the issue is more than that, right? It's not like just defining a distance measure. These clusters are not just singleton points, they are going to be subsets of the data. So how do you then define the the nearness of two clusters? Okay, so it turns out that's not kind of an easy question, and you can actually have multiple measures of nearness. Okay, so measures of nearness or distance. Okay, so one is you take your clusters. So remember that each cluster is a set of points. So let's call the set of points in one cluster by x, and the set of points in the other cluster Cj with x prime. So if I have x minus x prime, so I can take distance. You can take, L2 distance, L1 distance, whatever. But remember, x is one of the points in C1. So what you can do is you can take the minimum of these distances. X belongs to C1, x prime belongs to, or Cj. Okay, so I'm basically looking at all the points in cluster, and I'm looking at the minimum, the pair of points that are minimally separated from each other, which have the minimum distance from each other. Okay, and this is sometimes called dmin, CI, CJ. Okay, and this is called the single link. And it's called single link because, it really depends only on the smallest distance between the pairs of points. Okay. You can, instead of taking min, you can actually take max. X minus x prime, and this is similarly is called dmax. Okay, and this is called complete link. And so these, have different characteristics. If you end up looking, for example, at some points like uh, if my points are like this, right? So single link will say that, well, these two are close to each other. It actually says that since this point over here, and maybe these two are close, and it'll actually say that since these 2 points are close to each other, it'll actually merge these. Okay, and so it has this tendency to form long chains, and that's kind of why it's called single link. Okay, whereas if you look at Dmax, it's kind of trying to minimize the furthest pair of points. Remember that this is the distance measure that goes over here, right? Right. So you measure the distance using this, and then you find the nearest pair. So you find the minimum among all pairs of Dmax. Okay. So they have just different behavior. These are very much heuristics. Another one is dmean. So instead of looking at all pairs of points, I can just look at Ci, Cj, I can just look at the mean points, Mi minus Mj. So what I'm doing is I'm basically representing the set of points Ci by their mean. Okay, and the set of points Cj in Cj by the corresponding mean. Okay, so Mi is the mean of cluster Ci, and similarly Mj is the mean of cluster Cj. And then you have, you can you can basically cook up many different things. So one other thing that people use is the average, 1 divided by Ni and J, summation of, so you, instead of taking mean or max, you sum all the distances and you take the average distance. Okay, where Ni is the size of cluster Ci and Nj is the number of points in cluster Cj. Okay, any questions so far? And remember, so far these have only been heuristics, right? If you realize this situation is a little unsatisfactory, right? Because there is no kind of objective measure so far, right? So for example, in classification, we saw that, hey, maybe we want to minimize the training loss. Maybe that's not always good because of overfitting. So we have a regularization, right? Is there an objective function that we are trying to minimize over here? So there are now a whole bunch of other clustering methods, unlike the ones that I have specified so far, where there is actually an objective function. So let me give you a very common and popular objective function that is used to judge the quality of the clustering. Okay, so let me just write it down, and some of you might have seen it. I equals 1 through k. Okay, so objective function for k clusters. So suppose you're given, k clusters, each cluster being the set of points. Then I'm going to measure the width or scatter of each cluster. So if x belongs to Ci, I'm going to say that this is a measure of the cluster I. Okay, so this is, sometimes you can call it scatter or width of cluster I. Okay. And the smaller this is, the better the clustering is. And then you basically do it over all I to k. So one of the things that, of course, you should realize is that when I talk about clustering, it is a disjoint partitioning of the points. So there is no overlap. You can work with things like overlapping clustering, where a data point might belong to two clusters, but for now, we are not talking about there being any overlap. Okay. So Mi is centroid or mean of Ci. Okay, and let's call this J because we'll need to refer to it. So this is one of the commonly used objective functions. Clustering is actually a very hard problem, right? If you think about it, when we looked at classification, so far in logistic regression, SVMs, least squares regression, all our loss functions were convex. And so we can actually find the global minimum of the supervised learning objectives. Well, it turns out that even this simple objective this is very hard to find the global minimum. So all the algorithms will end up being heuristics, right? Because there's just a exponential number of partitions of a set, and it's really not possible to find in polynomial time the minimizer of these objective functions. But let's see how we can get a algorithm that is guided by an objective function to get to a heuristic, which is, at least you can reason about it. Okay. So one goal we can have, okay, is, well, I mean, the ultimate goal, let me write that down. Find clustering into K clusters that minimizes this objective. Okay. So, like I said, this is a very hard problem. This is an NP hard problem. So we cannot actually, will not really be able to get any polynomial time algorithm to give us the solution. And later on, we'll see that there's a more direct method which does not do agglomeration, but actually divides the data set. So it's a partitional algorithm, right? It's very famous. It's called the k-means algorithm. So we'll come to that later in this class. But right now, let's look at agglomerative clustering. And let's see if I can actually take my agglomerative clustering method and get an algorithm that greedily optimizes J. Algorithm that greedily optimizes the objective. Okay, well, what do I mean by that, right? At every step of the algorithm, we are basically merging two clusters into one. So we can retain the same structure. So still agglomerative, still hierarchical agglomerative, but maybe what I can do is this criterion for find the nearest pair of distinct clusters, right? I can actually be a little bit more principled about that and say that let me try to minimize J. So what do I mean? Okay, suppose I have cluster CI. Let me call its width or quality or objective function as Ji. And that's like I defined before. It's exactly this quantity. Okay, so it's x belongs to Ci, x minus mi square. Okay, and I'm just emphasizing that, this is the 2 norm. That's what is typically used. Then I have JL, which is the Lth cluster. X minus ML square. Okay. Now, suppose we merge Ci and Cj. Okay. Then we'll get a new mean, right? So remember, this is the mean of cluster Ci. This is the mean of cluster Cl. Okay. But the new mean, so remember, so just to make sure that you understand, or just to give the details, right? Mi is equal to summation of x belongs to, summation of x such that x belongs to Ci, and it's 1 divided by Ni. And Mj is equal to 1 divided by Nj, so it's the arithmetic mean. X belongs to Cj. Okay. Well, when I merge this cluster Ci and Cl actually, not J. Okay. Then the new mean will be, let's see, let's call it Mi hat, right? It'll be the summation of all the points in now the merge cluster, right? So I can write it as summation of x belongs to Ci, okay, and x belongs to Cj, and 1 divided by Ni plus Nj, right? But I can also write it as in terms of Mi and Ml, okay? So let me write it out first. Ni, Mi plus Nl, Ml. So if you just think about it, this is now getting the summation of all the points, this part, right? Ni times Mi is equal to summation of all the x's, and Nl, Ml is the summation of all the x's in cluster L. And the total number of points is Ni plus NL. Okay, so that's the new mean. And I can actually write it. Let me rewrite it in a way that will make it easy for us to do the manipulation that I want to do, right? So I can write it as a modification of Mi. Okay, and so what I can essentially do is, maybe I'll just write it out, right? So if I do the following, Ni Mi plus NL Mi, so I'm just adding NL Mi plus NL ML minus NL Mi. So I haven't changed anything. I've just written it like this. I've just added this and subtracted this. So I haven't made any change. But that gives us Ni plus NL Mi, and I can divide it. So I can write it as Mi plus, what do I have over here? NL, ML minus Mi divided by Ni plus NL. Okay. And similarly, I can write it as a modification of ML. Okay, and it'll be ML plus Ni divided by Ni plus NL, Mi minus ML. Okay, so there are two different ways that I can write it. Okay, before merging, okay, my objective is Ji plus JL for cluster I and cluster L. New objective after merging. So suppose we merge Ci and Cl, right? After merging is going to be the following. Summation of x belongs to Ci, x minus m, sorry, too much in a hurry, x minus mi hat square plus summation of x minus m I hat. Same thing, except here the summation is over cluster L. Okay. And what I can then do is I can substitute this. Okay. Remember, mi hat is this value. So in the first term, what I'll do is, so there's a lot I have to write. So let me start over here. Oh, maybe not that much. Okay, so I can write it as summation of x belongs to Ci. And you'll see why I'm doing it in a minute. So norm of x minus, and I can substitute mi minus NL divided by NI plus NL ML minus MI. And then on the other side, I can do summation of X minus. So what I'm doing is, I had basically substituted this over here, and now I'm substituting this over here. Okay, and it is ML minus NI divided by NI plus NL MI minus ML square. Okay, so that's the change. That's the new objective function. Okay, and now what I will do is I'll basically just use the following, right, which is the norm of A minus B square, the 2 norm, is equal to A minus B transpose A minus B is equal to norm of A square plus norm of B square minus 2 times A transpose B. So I'm basically going to apply this over here. So let me do that algebra. Okay, so be patient. So I can do this. I have this. This corresponds to my A. This corresponds to my B. Okay, so I have X minus MI square plus B square, which is NL divided by NI plus NL square times ML minus MI square. Okay, and then I have this 2 of A transpose B. So 2 of this transpose times this transpose, this. So minus 2 times X minus MI transpose ML minus MI. Okay, and then I have this term. So let me do that. X belongs to CL. X minus ML square plus. So remember, all this is within the summation sign. Similarly over here. Okay, so I have Ni divided by Ni plus NL square. Please keep me honest in case I make a mistake, which is very probable. Okay, and then I have 2 times X minus ML transpose MI minus ML. Now, notice the following, that over here, this is a summation of all the points, right? This is just Ji. This quantity, right, along with this summation, is just Ji. So I can write this first term as Ji. Okay, and why don't I do the following same thing over here? This term is JL. So I have, what the heck happened here? JI plus JL. What about the other terms? Well, the other terms are a little bit more complicated. Okay. But notice this term over here. This ML minus MI is actually constant for the summation sign. And if you think about it, summation of X minus MI, X belongs to CI, is actually equal to 0. because that's actually the very definition of MI, right? That MI is equal to 1 divided by n I of summation of x. So since that is 0, okay, since that is 0, from here onwards, right? So this, because of this whole summation sign will be 0. This is equal to 0. And similarly, this term, this whole term is going to be equal to 0. Is that clear? Okay, so hopefully it's clear. That's the definition of MI, right? So because if I write this out, summation of x belongs to Ci, right? Minus NI equals 0. So this is that Mi is equal to 1 by Ni, summation of x belongs to Ci. So the mean always has this property that x minus Mi, x minus mean, is going to be 0 when I sum it over all the points. Okay, so we've been able to delete these, remove these quantities. So now I have this. So remember that this is now independent of x belong to Ci. So each term will get added Ni times. So it'll be Ni NL square divided by Ni plus NL square ML minus Mi square. So that's this term. And then this term will give us NL Ni square divided by Ni plus NL square Mi minus ML square. So if I look at this, okay, it has this in common. So I can write this as Ni and L. I can take this out common, Ni plus NL square, and then I get, and also ML minus Mi is common. And what I get is NL plus Ni. NL from here and Ni from here. Okay, and since I have NL plus Ni here, it cancels out. So this is Ji plus JL plus Ni and L divided by Ni plus NL. Mi minus Mj square. So notice what happens, right? Whenever you merge two clusters, my width is actually going to increase, right? Because it's a bigger cluster, right? So when I merged Ci and Cl, I get this increase, right? So I can say that this is my distance measure or the square root of this. So d-opt, so when you try to optimize this objective function, is square root Ni and L divided by Ni plus NL times Mi minus Mj. Okay. So this is another distance measure. And if you look at it, well, it's actually kind of close to some of the heuristics. So one heuristic we talked about, right, which was this one over here. Here we were doing just Mi and Mj. But what we've seen is that if we say that this is my objective function that I want to try to minimize, that's the definition in some sense we are positing for the quality of a cluster, then you actually get slightly modified rule, which is count. Okay. Like I said, I'm not going to spend a whole lot of time talking about clustering. There's a question in the chat. Is he cutting out for anyone else? I see. Am I cutting out?
Yes, a bit.
So what's happening?
Cursor is not visible. The cursor is not visible when you point out to.
Oh, really? Okay. Yeah, sorry. I'm actually using a different laptop today. It's a slightly different arrangement, and I have my. Usually, what I have is I have my iPad connected to my laptop, to my usual laptop. Um, but today, actually, I've set it up so that I have two different connections. So one from my iPad and one from my laptop. So apologies if you're seeing kind of a little bit of breaking up or cutting out. But I'm just working with a different laptop today, so hopefully it's not too bad. And looks like from the comments that maybe it's only sometimes when it gets worse. I did get a notification on my laptop saying, or on my iPad saying there was a low bandwidth connection for some time. So it could be that, it was a momentary issue. Okay, so well, we've seen that. Uh, um, um, we've seen the definition of or one definition of a good clustering, right? So let's now talk about not agglomerative algorithms, but I think algorithms which are quite popular, partitional algorithms. Okay, and these are sometimes called top-down clustering, or as opposed to bottom-up clustering, which was the agglomerative algorithm. Okay, so there's a very popular method which any machine learning student should know about, and that's called the k-means algorithm. And even in deep learning, in various aspects of deep learning, sometimes you use k-means to either pre-process the data or do something else. So it's actually a good method to know about. So sometimes when people talk about k-means, so as the name says, it's trying to get k clusters, and it uses means or centroids, which we've already done, even in the context of agglomerative methods. But the k-means algorithm is going to be a divisive or maybe I shouldn't use that word, but a top-down clustering method, right? Divisive as in it breaks things up into multiple parts, right, or partitional, right? And then there is a k-means objective. And you should actually realize that there's a difference between them. So the k-means objective function is exactly what I mentioned before. So it's exactly the same as over here. Okay. So let me just write it again over here. K-means objective is J is equal to summation of I equals 1 through K, summation of X belong to Ci, X minus Mi square. Okay, and remember, just to remind you, Xi belongs to Rd. Okay, and these are quite different. So the k-means algorithm tries to directly minimize the k-means objective. But like I said, the k-means objective is a hard objective to optimize. It turns out that it's an NP complete problem, right? This method that we talked about, the agglomerative, was only using this objective in merging the clusters. But the k-means method actually tries to directly optimize this. So let's see how it does it. Okay. And first, let me just kind of give the algorithm. It's very, in a way, somewhat intuitive. Okay. So let me give the k-means algorithm first. Okay. So it starts with some partitioning of the data into K clusters. K clusters, okay? And let me call them C1, and with superscript, I'll denote, in some sense, the iteration number. So right at the beginning, these are the clusters. Okay, so remember there are K clusters. Okay, and I'll set T equal to 0. And T is basically the superscript that I'm using. Okay, given these clusters, okay, you already have a clusters. What it does is it computes so it calculates the mean centroid of each cluster. CIT. Okay, so I have clusters at iteration T, and I basically compute the mean of the ith cluster. Okay, and I'll put the superscript T, 1 divided by Ni T, summation of x belongs to CIT. Okay, and remember that Ni is just the number of elements in the cluster, I. Okay, so I basically do this for I equals 1 to K. There are K clusters. So given a partitioning, I compute the means. Okay, and then each data point asks the question, okay, which is what mean vector am I closest to? And then depending upon the answer, it reassigns itself to the nearest cluster centroid. Okay, so let me write out what I said. For each x, find its nearest. So find its, I'll just call it the cluster index. So let me call I star as the cluster index. So the I star x, I star for point x. I'm going to look at all the distances, x minus mi, from all the K clusters, and I'm going to take the minimum. And the minimum index is the argument. Okay? And I'll illustrate this. And then what it does is, it then updates the clusters. CIT is basically all the points x such that the cluster index is I. And then it repeats steps 2, 3, and 4 until, and we'll talk a little bit about it, until convergence. And the convergence is typically when points maybe they don't move at all from one cluster to another. Or you could have some other criteria. Okay. So this is the algorithm. Kind of simple algorithm, but not that easy to always understand what is going on, right? So let me kind of just take an example where you have this. Well, let me make it a little closer. Okay. Or so I'm making it that far. So how many clusters do you see? Most people will say that, it's two clusters, one here, right? But suppose my clustering at that time t, so let me just also draw it over here, right? Which is, let me see if I can actually do this. Okay, and I copy it and I paste it. Oh, I did it. Okay, so okay, so at time t, at iteration t, and what we'll see what happens at iteration t plus 1. Okay, at iteration t, suppose that my clustering was this. Okay, so this is the ith cluster at iteration t, and this is the jth cluster at iteration t. Okay, let's just think about the algorithm, right? So the algorithm, I have some clustering, and it computes the mean of each cluster. So what is the mean of this cluster, Ci? Well, it'll be somewhere over here, right? So this would be maybe, maybe I'm being generous. Maybe it's actually a little bit, it's the average of all the points, right, in this cluster. So maybe it'll be a little bit over here. Okay, so this will be MIT. And this will be MJT. So step 2 is done. And then step 3. So for each point, so let's say we have this point. What is the clearest centroid? Is this, right? So it will look at the distance from here to here, the distance from here to here, and it'll just say, okay, this I star x is equal to I star x equal to I because this distance is smaller than this distance. And so for all these points, it'll be the same. What about this point? It computes the distance to mi, computes the distance to mj. And so in this case, the distance to mj is actually smaller. Okay. So what will happen is at this point, I star x will become equal to j, which means that, and over here, all these points will also have this centroid being closer than this centroid. So at the next step, step 4 will give these clusters. Okay, so this is an example where this algorithm actually works. It doesn't always work because, like I said, it's an NP-hard problem. But in this case, it gives us the right answer. Any questions on the method so far? Okay. Now the question is, what does this method do, right? I mean, yeah, we saw on this particular example that it does the right thing, but what can we say in general? Okay. So k-means has a property. Okay, which is that k-means monotonically decreases the objective function. And remember, my objective function was j. So, I can just say property. Okay. That doesn't mean that it gets to the global minimum. It can be a descent method, but it may not reach the global minimum, and that's what happens over here. Okay, so let's see. Okay, so what we are saying is that jt, the objective function at iteration t, is summation of I equals 1 to k, summation of x below. I'm just using the definition of j. Okay, and the claim is that jt plus 1 is less than equal to jt. And that's the question mark. Okay, so let me give you a proof that that is indeed the case. Okay, let me use my newfound power and copy this. Nope, yep, copy, paste, perfect. Okay, so JT is the definition. Okay, and now let's see. I have this step in the method, right, which is that at t plus 1 iteration, or when you found the cluster index, then it is the minimizer, minimum among all the distances to the centroids. Okay, so what you can then see is that if I replace this, okay, by, so I do the same kind of thing, except I will change this x minus mi to be x minus mi star x. So same ordering of points, summation of I equals 1 through t, summation of x belongs to ci t. So I'm considering all the points x's in the same order as they were done before. But instead of this, I've replaced it with this. But since I star x is the index of the closest centroid, I know that this inequality holds. Is that clear? Right? I've just replaced I with I star x, and remember that I star x is defined as the index of the nearest centroid. Okay, so this is by step 3 of the k-means algorithm. Okay, now I'm just going to rearrange everything. Okay, so instead of writing it in terms of this was I equal to 1 to k. Okay, so what I will do is, I'm still considering k clusters, but I'm actually now going to consider the order of the points according to the cluster at step t plus 1. Okay, so that's all I'm doing. Okay, so I've just rearranged everything. Okay, and now because of the property, so you must think, okay, why were we taking the mean of all the points? Why not do something else, right? I mean, maybe I could have done some other statistic like median or something, or whatever you want to do, right? Some other operation. But if I have a collection of points, okay, so if I have a collection of vectors, right? Suppose I have a collection of vectors, I have y1, y2, yn, and I try to solve this problem. Minimize z, summation of I equals 1 through n, yi minus z. Then the optimal Z is just the mean. So the mean is the best representative, and this is the reason why. That's why it's kind of like the center of gravity or so, right? So because of this property, if I now take this and I rewrite the right hand side as I equals 1 through k, okay, x belongs to ci t plus 1. Remember, ci t plus 1 is defined as all the points I star x equals I. Okay, so now I'm recalculating the mean for all these points. And because of this property, the new mean, okay, sorry, I made a typo. The new mean is mi of t plus 1. This holds. And this quantity is exactly j of t plus 1. Okay, so that completes the proof. Hence, k-means algorithm. So remember, I made a distinction between the k-means algorithm and the k-means objective. Hence, the k-means algorithm monotonically minimizes the k-means objective function. Okay, and then there are other properties that k-means has. So in particular, k-means separates data by linear surfaces. Okay, and in particular hyperplanes. And the way to see it is, suppose k equals 2. If I then look at, the locus of all the points which are equidistant to locus of all the points equidistant to M1 and M2, sorry, M1 and M2, right? It'll be x minus M1 square equals x minus M2 square. Okay, and that is the equation of a hyperplane because the quadratic term will cancel out. Okay, so k-means is a kind of a very widely used algorithm. It has some nice properties. It also has actually quite a lot of drawbacks. So many times people will, sometimes you can get empty clusters. The algorithm, whenever you run it, it'll give you a different result if you change the ordering of the points. But still, it is a very widely used algorithm and something that everybody should know about. Okay, so that comes to the end of today's lecture on clustering. Any questions on the material?
Any heuristic of how to pick the K?
Oh, yeah, that again is a very, very difficult question. So theoretically, you can come up with different heuristics. Practically, it actually becomes very difficult. I actually have done quite a lot of research in that area a long time ago, and it's very difficult. So one of the kind of like the heuristics is that as you increase k, the objective actually declines, right? Because you are now getting, so take the extreme end of n clusters, the objective function will actually be 0, right? So the objective declines, and typically, as you, so objective function and k, the objective kind of declines like this. And many times people say, oh, you should choose k to be somewhere around here, which is like the is also called the knee of the curve. But in practice, these is actually very hard to get it to work. So typically, people will just use either they'll know what k they are looking for, or they'll use some arbitrary k. And then remember, you can always hierarchically divide things, right? So you can actually get a tree by doing partitions repeatedly.
Thank you.
Any more questions?
May I
Okay, so let me. Yeah, sorry, was there another question?
ask a question about the previous material, like the SVM?
Sure.
And
Oh,
the SVM, we can do the kernel trick, and therefore the advantage over the perceptrons is that we can do non-linear, separable problems with.
yes.
Uh, is there any way to basically pull off the kernel trick in the perceptrons? I was just
Oh,
wondering.
yeah. You can. I haven't thought of it in a long time, but yeah, I believe you can. I believe you can, but I actually am now that I may look into it and let you know, but actually maybe not, huh? Because a perceptron explicitly considers constructs like W, right?
Right.
And the W is in the feature space. I remember looking at this a long time ago. There may be an alternate algorithm that is like an online version of kernel SVM. Because if you think about perceptron, it so yeah, I mean, I'm going on a little detour, but I'm trying to answer Hormoz's question, right? So it turns out that there is a variant of perceptron called Adatron that actually gives you the maximum margin hyperplane. Okay, so you can think of that there is an online SVM algorithm, right, that gives you the SVM, which is it is like the perceptron. Okay,
Hmm.
so I'm thinking that there's probably an online version of the dual SVM that actually gives you the maximum margin hyperplane. And there, I suspect that you can use the kernel trick. Because for the primal problem, you see, the thing is that you don't want to explicitly construct the feature space.
Exactly, because that was
Yeah, yeah, that was what. But I think so. I think there is there is probably an online kernel SVM method which is similar to the perceptron, and so what that'll do is construct alphas, and it'll visit each point repeatedly and modify the decision. Right? It won't explicitly construct a W. But honestly, Hormoz, I haven't thought about research in SVMs for 10 years because everything is deep learning now.
yeah, makes sense. Thank you.
Okay, so I can think about it and get back to you. And actually, that kind of concludes this lecture. And in the we've already talked about deep learning a little bit, and the second half of the course will be much more about deep learning, and then you'll also do your projects.